Hello. In the previous video, we studied Rn and vector operations like addition and scalar multiplication. We discussed 10 properties of addition and scalar multiplication. We also talked a little bit about the set of matrices, because we know how to add two matrices of the same size and how to multiply a matrix by a scalar. So on the set of matrices, we also have two operations, right? Vector, or we say matrix addition and scalar multiplication. And we mentioned that those operations satisfy, 10 properties, okay? And today we study general vector spaces, okay? Let's give some definition for a set to be a vector space, and we consider some examples. Now, suppose that we have some set V, and on this set, we define two operations, vector operations and vector addition and scalar multiplication. Okay, and if these operations satisfy 10 properties for every u, v, w, and any scalar c and d, then V is called a vector space. We have 5 properties for addition right here. Okay, the first property says, V is closed under addition. Okay, the second property says about commutativity, means if you interchange position of u and v, so you get the same sum, and of course this vector is in V. The third property is associative property. So you might add, these two vectors, right? Or you might, just do addition of u and v first. And the fourth property is about additive identity. That means for every u, there exists, a zero vector, such that for every u in V, u plus 0 is just u. So this plays the role as 0 for addition. And the last property is about additive inverse. For every u in V, there exists a vector denoted by negative u, such that u plus negative u is 0. And of course, in this case, you have 0 vector, not number 0, okay? That is vector. This is also vector, okay? And we still have other 5 properties for scalar multiplication. The first property says, yes, V is closed under scalar multiplication. The second case is distributive property. So actually these two properties are distributed, right? So you might distribute this. You have Cu times plus Cv, and if you have two numbers C and D, you might distribute U D with the UC. Okay, and the fourth property is associative property. So you may break this like C and then times du in here. And if you multiply u with 1, you get u. That is about scalar identity. So if you pay attention, these 10 properties are the same, are almost the same, with properties for Rn. We discussed about that last time, right? So, that is general axioms for vector spaces, right? So that means in order to determine if a set is a vector space or not, we need two operations, right? Addition and scalar multiplication. And together with the V, now if scalar multiplication and addition satisfy 10 properties like this, then this is a vector space. Okay, so that means Rn is a vector space, right? And the set of matrices n by m together with standard matrix addition and scalar multiplication is also a vector space, right? Now let's consider more examples about that. So along with n by m, we have the following vector space we call, Pn. Pn is the set of all polynomial of degree less than or equal to okay, let's mention this, less than or equal to n. Okay, so I can write like this: Pn is the set of polynomials. So I have a0, a1x plus so on plus an x to the n, right? Where I are real numbers, so are from 0, 1, and n. So this is the set of all polynomials of degrees less than or equal to n. We know with the standard, on Pn, we have the following addition. So we say, let's say a0 plus a1x plus so on plus anx to the n plus b0 plus b1x plus so on plus bn x to the n equal to a0 plus b0. You just add corresponding, right, coefficients, right, of all terms x and x squared and so on. So you have a1 plus b1x so on plus an plus bn x to the n. So this is the standard addition, right? And the scalar multiplication is now lambda a0 plus a1x plus so on plus a n x to the n is lambda a0 plus lambda a1x plus so on plus lambda an x to the n. Okay, with this, addition and scalar multiplication, the set Pn will be a vector space. It is easy to check. Okay, and if we pay attention on this, we might have some, let's say, some relation between Pn and Rn. Look at this. So I had to mention this, right? In order to determine one vector, right, in Pn, we need how many numbers? We need n plus 1 numbers, right? Is that correct? You need a0, you need a1, you need an. So basically you have n plus 1 numbers. And of course, you cannot interchange. When you interchange the position of a0, a1, you get another polynomial. Is that correct? So basically you may have the following vector. Like I can write, the following relation, right? Let's say P n, it's just an element of this, okay? They are different a little bit. Pn belongs to Pn. Now that is corresponding to some vector in Rn. Let's say A in Rn plus 1, right? Because you have n plus 1 coordinate. So that is like A equal to A0, A1, and so on, An. You see this? So basically, in order to give one polynomial of degree less than or equal to Pn, is enough to give one vector in Rn plus 1. Does that make sense? So you can see some relation, right, between Pn and Rn plus 1. So if I give you one polynomial, you just collect all coefficients and you get a vector in Rn plus 1. And if I give you a vector in Rn plus 1, you may use those numbers, right, as coefficients for a polynomial in Pn. So we have a feeling that actually these two vector spaces are the same. Is that correct? Is that correct? Of course, they are different in nature, right? Because one vector space have vectors like in this form, but another vector space have vectors at polynomials, right? So like this form. So it seems like that they are different in nature, but from this relation, we have a feeling that actually they are the same, aren't they? We'll see that later. But sometimes we use this relation to solve problems. Agree? If you remember calculus 1, right? When we were talking about one-to-one functions. One-to-one functions means, if you have, this is the domain and this is the range, right? You have some function f in here, f for each x in here, there is only one y such that y equal to f of x, and for each y in the range, there's only one x in here such that x equal to f to negative 1y. So I hope you remember this picture, right? In calculus 1 we learned that. So this is kind of one-to-one map between the set of, or between the vector space of polynomials of degree less than or equal to n and Rn plus 1. Okay, so if you pay attention on this, like addition in Rn plus 1 is almost the same like this, in Pn. Does that make sense? They are corresponding, right? They are corresponding. All right. Now let's talk about another example. Let's denote by C negative infinity power to infinity the set of continuous function on negative infinity to power to infinity, means on the whole number line. Okay, and let's define the following addition. And this addition also, is standard one, right? So f of a plus g, the element f g x equal to fx plus gx. And scalar multiplication is lambda f at x is just lambda times f of x. Okay, don't forget this is an element, right? It just we define that addition, and here is scalar multiplication. So it's obvious that with this addition and scalar multiplication, C negative infinity to power to infinity is a vector space. Okay, so it seems like with those standard operations everything looks good, but we have two questions in here. The first question, so regarding the set of Pn, right, with standard addition and scalar multiplication, you say you have all polynomial P x of degree less than or equal to n. So what happens if we deny this condition? Let's pick polynomials of degree equal to n. Okay, so let's draw it out, right? So suppose this is the set Pn, right? This is, all polynomial of degree less than or equal to n. Then in this set you have another subset. Let's say, all polynomials of degree equal to exactly n. Does that make sense? So the question is it a vector space or not? Let me denote this by Pn prime. How about that? So it turns out that Pn prime is not a vector space. Set of all polynomials of degree n is not a vector space. With, of course, with standard, with standard operations over Pn. Why? You can pick, two polynomials, right? And you have to show that actually that set with those operations will not satisfy at least one properties for addition or scalar multiplication. Does that make sense? So, we just need to give some counterexample. That means, that set does not satisfy one of these 10 properties. So it is pretty easy. Look at this. You might pick a vector, let's say a0 plus a1x plus so on plus an x to the n, right? And in this case, I suppose that an is not 0. Another vector is negative a0 plus a1x, negative, minus, so on, minus an x to the n. And when you sum them up, you get 0 plus 0 plus so on plus 0. That means you have a 0. But the set of all polynomials of degree n does not contain 0, right? Which is not in Pn prime. So that means the first property of addition fails. You see this? So that's why, this set is not a vector space. Does that make sense? So from here I get Pn prime is not a vector space. So see, sometimes we change a little bit, right? We change a little bit and you don't have vector space anymore. But it is reasonable, because, if you pay attention, so 0 is right here, right? 0 vector is right there. 0 does not belong to this. So that is not a vector space. Okay? I might give you another example. And that is very, that is well-known example. When we consider, equation of straight line on the plane. Okay? Let's say R2. We learned about this already. Last time you have x, y, so that is R2, right? Let's say you have some straight line like this, and another straight line which pass through the origin. Okay. Okay, let's pick like y equal to 1/2 x, okay, and this is y equal to x minus 1. How about this? Let's see. No, plus 1. Sorry. Okay, not exactly, but yeah, let's pick two examples. So, what is the difference between these two straight lines? This straight line passes through the origin. This straight line does not pass through the origin. Is that correct? So, if I look at, the set like this, for example, let me denote by L1. This is L1, this is L2, right? I want to see L1 and L2 are vector space or not with the standard operations over Rn. So we need to check that. Is that correct? Okay, let me rewrite R1 as xn 1/2 x. Right? So you might describe R1, this is the set of all points x 1/2 x, where x is real numbers, right? And R2 is what? Is all xn x plus 1, where x is real number. Does that make sense? Because you need to describe all points, right? In here or in here. So the coordinate is x, so from here you have y equal to 1/2 of x. So this is x 1/2 of x. And in here you have, for x in here you have y equal to x plus 1. That's why you have x and x plus 1 right here. All right, look at this. So I bet you may check, 10 properties of L1. All right? And, L1 satisfies 10 properties. You may do that yourself. I very hope that. Like, look at this. So let me check all of them and then we'll see, right? So I will write L1 in here. That is x 1/2 x, right? So what I mean, x plus u plus v is in v. Okay, so the first property, let me erase this. All right, so the first property, u plus v. That means if I pick one element, x and 1 over x, and I add with the second one is y, 1 over y, or let's say x prime, okay? So when you add them, you have the following: x plus x prime and 1/2 x plus x prime. You see, this vector also has the form of this. Is that correct? So that means this vector is in V. That means the first property is satisfied, right? Now, if you interchange the position of x and y, or u and v in the addition, of course, you can see from here, right? There's nothing changed. If you interchange x and x prime in here, you get the same vector. So that means the second property is also satisfied. The third property is also satisfied. Look at this. So let's say you have x1 1/2 x1 plus parenthesis x2 plus x2 1/2 x2 plus x3 1/2 x3. Okay, so if you add these two vectors first, you get x2 plus x3 1/2 x2 plus x3. Is that correct? So, and then you add this vector with the first one, you get x1 plus x2 plus x3 and 1/2 x1 plus x2 plus x3. Okay, that's what you have on the left hand side. Now you check the right hand side, u plus v plus w, right? So you add the first two vectors. If you add x1 1/2 x1 with x2 1/2 x2, right? And then you add the third one. We just need to check that carefully, okay? So you add these two vectors, you have x1 plus x2, 1/2 x1 plus x2. And then you have x3, 1 over 2 x3. You get x1 plus x2 plus x3. And here you have 1/2 x1 plus x2 plus x3. Look at this. If you compare this guy with this guy, they are the same. Is that correct? So that means the left and the right hand side of this identity are equal. So the third property is satisfied. it's, it's long, but it's easy. Does that make sense? All right, now let's check the fourth one. V has a zero vector. So the general form of those vectors look like this. So when x is equal to 0, you have 0 vector, right? And we know from Rn that, you add 0 vector, you get the same vector. So the fourth property is also satisfied. The last property is obvious because, if you pick any vector x, 1/2 x, you just, add with negative x and negative 1/2 x. Since this is the standard addition in Rn, you get, x minus x, 1/2 x minus 1/2 x, and that is 0. So, 5 properties for addition are satisfied. Similarly, you may check all these, properties. That means L1 is a vector space, right? With standard addition and scalar multiplication in R2. So we are good, okay? L1 is a vector space. Now look at this. L2 is not a vector space. Why? Because L2 does not have 0 vector. Right? Does that make sense? So I don't know, but I have feeling that actually that is not a feeling, that is the exact information about a set. If a set is a vector space, that should have 0 in that set. But if that set does not have 0, that is not a vector space, right? So if you look at this picture, right, and the example right here, you see? The example right here. Because this set is not a vector space because Pn prime does not contain 0 polynomial, which is vector 0, right? And on this guy, all those straight line with the standard addition and scalar multiplication will not be a vector space because does not pass through the origin. That means does not have 0 vector. Okay, we will learn about subspaces later, but that is the very important criterion, right? If the set does not have 0 vector, that will not be a vector space. Don't forget that. So we already have good examples. Right now I want to show you 2 more examples. The first example is about Rn, but we will change operations. Okay, we have standard operations like we call standard because that's how we learn, right? How to add 2 vectors. That means you just add corresponding coordinates. And how to add 2 polynomials, so you just add corresponding coefficients, right? Now let's change operation. You have the same set, right? With the standard operation, that is a vector space. But when you change at least 1 or 2 operations, maybe this set with new operations will not satisfy 10 axioms, or just at least 1 axiom in the set in 10 properties. Does that make sense? In that situation, that set will not be a vector space with respect to new operations. Okay, so look at this. We can pick R2 because that is the easiest case, right? It is similar to Rn. So in R2 I will define let's define the following scalar multiplication. C x1 x2 is equal to C x1, and here we have 0. Okay, so, and we keep addition, x1 x2 plus y1 y2 is just, x1 plus x2 and y1 plus y2. Okay, so we have new operations in here, and we need to check R2 with this operation satisfy 10 properties or not. Okay, so with this addition, so we don't have any problem with that because that is standard addition, right? So we might have problem with scalar multiplication, right? So let's check 5 properties of the scalar multiplication in here. Where are they? Right here. Look at this. So let me write the scalar multiplication. We just define Cx1 x2 equal to Cx1 and 0, right? So everything in the second coordinate will be 0. The first property is obvious. Is that correct? Because you multiply Cx1 0 is also in R2. The second property is also okay. Look at this. Because you have some C, right? You multiply with x1 x2 plus y1 y2 in here, and you take sum first. You have x1 plus y1, x2 plus y2, right? And according to this multiplication, you have C x1 plus y1, and here you have 0. Does that make sense? So that is the right hand side, the left hand side part, right? This is the left hand side, so this equal to this. So if you do almost the same thing for the right hand side, you get C times this one and C times this one. You get exactly this vector. Let's check that. You have C x1 y1, that is C x1 0. You have C, no, sorry, here I have x2, okay, here, and here I have y1 y2, that is C y1 0. And then you sum them up, you get exactly this vector. Does that make sense? So you have C x1 plus x2 y1, sorry, 0 in here. So that is what you got. Write this. So the second property is also okay. The next property is also similar to the second, so I will not check that. The fourth one is also the same. Okay, the only thing is this, the last property. You have 1 times xy. What is that? According to this operation, you get x and 0, and of course that is not xy when y is not 0. So that means the new operation in here does not satisfy the last property of scalar multiplication. R2 is not a vector space. Does that make sense? So with this addition, R2 is not a vector space. So you see, a set is a vector space or not. It really depends on how we define scalar multiplication and addition. Now let's consider R2, but we change the addition. Okay, so we keep the standard multiplication like this, but the addition is defined as follows. So you have x1 plus y1 y2 is 2 times x1 plus y1 and x2 plus y2. So we just double the x coordinate, the first coordinate, okay? And we'll see if R2 together with these operations is a vector space or not. We just need to check that. Let's go ahead to check 5 properties of addition, right? Because we don't have any problem with scalar multiplication. So the first property is okay, right? That is closure under addition, because we have x1 x2 plus y1. y2 is 2 times x1 plus x2, y1 plus y2. So this is a vector in R2, which is good. The second, commutative, is also okay, because when you interchange these two vectors, right, you just need to interchange. I think I do something wrong here. He should be y1. He should be x2 plus y2. I guess that's how we define, right? Yes, x2 plus y2. Sorry for that. So here you should, let me make that clear. X1 plus y1 and x2 plus y2. So when you interchange u and v and u in here, right? So you just interchange x1 and y1, x2 and y2. Does that make sense? So the second property is also okay. Now let's check the third property. Okay, so you have 3 vectors. Let's say u is x1, x2, v is y1, y2, and z is z1, z2, w. Okay, and let's just compute the left hand side and the right hand side parts. Okay, the left hand side part would be equal to u is x1 x2 plus I have y1 y2 in here plus z1 z2, right? So according to the addition, this is equal to 2 times y1 plus z1 and then y2 plus z2. Does that make sense? So you add with x1 x2, and according to the addition, I have to double, right, the first coordinate. That is 2 times of x1 plus 2 y1 plus z1, and here I have x2 plus y2 plus z2. So this is the left hand side part. How about the right hand side? uv plus w. Look at this. You have x1 x2 plus y1 y2. So we add 2 vectors first, right? Plus z1 z2. So according to the addition, I have 2 times x1 plus y1, and here I have x2 plus y2, and then plus z1 z2, and then again according to the addition I get 2 times, right, of 2 x1 plus y1 plus z1. That is the first coordinate, and then the second one is x2 plus y2 plus z2, right? Now we just need to compare this guy with this guy. The second coordinate are the same, which is good, but the first coordinate are different. Look at this. They are different, right? So I have, in one side I have 2 x1 plus 2 y1 plus z1. In another side I have 2. We have 2 x1 plus y1 plus z1. So if you just erase, right, 2 in here, you simplify that, you would get the following. Let me erase, just erase like this. And here, erase this. Here I have 2 times, and here I have this. And it's obvious that, these two numbers are different. Does that make sense? So unfortunately, the third property is not satisfied. Okay, so we'll see. Actually, the fourth property is not satisfied either. Unfortunately, we don't have zero vector such that for every u and in R2, u plus 0 equal to u. Why? Look at this. So we suppose that, I cannot use 0, 0. I just use, x0, y0 is, let's say, 0 vector. Okay, we suppose that, this is a 0 vector such that, sum of this vector with any vector will be the same, right? Such that x0, y0 plus any u, let's say u1, u2 is equal to u1, u2. Does that make sense? So according to the addition, the left hand side should be equal to 2 times x0, u1, and here y0 plus u2 equal to u1, u2. So you compare two vectors in here, their corresponding coordinates should be equal, right? Then you have the following one. From here, you get 2x0, here should be plus u1 equal to u1. And then y0 plus u2 equal to u2, right? So from the second equation, you see that actually the u2 is 0, right? Y2 is 0. From here, you get y0 is 0. Y0 is 0. And from the first one, I have 2x0 equal to negative u1. But this is for any u1. Because, that property says, there exists a 0 vector such that for every u in V, u plus 0 is V, is u. Does that make sense? So that means, this should be equal for every u1, but that is impossible. That is impossible. So, there is not any vector like that. We have to pay attention here. They say 0 vector, right? 0 vector, but depends on the addition. So if here you pick 0, 0, again, 0, 0 will not satisfy that. Does that make sense? Because, if you pick 0, 0 in here, so you had the following expression. What is 0? 0 plus u1, u2. That is 2 times u1 and then u2. And of course, that is not equal to u1, u2 if u1 is not 0. So, unfortunately, when you change the addition, so R2 is not a vector space. Okay, so I think that, we understand the definition of a vector space, and we know that a set is a vector space or not. It depends on, operations, addition and scalar multiplication, and depends on how we define those operations. Okay, so I stopping here. If you have any questions, please feel free to let me know.